In this chapter section, you will learn about the systems that involve with two or more chemical reactions that are in equilibrium. Those reactions that we are going to focus on would be the solubilities and also the acid-base chemistry. We're going to combine both of them. The details of this chapter section can be found in the OER textbook, chapter 16.3. In chapter 14.8, we learn about salt that can be pH neutral salt, acidic salt, or basic salt, and those salts are ionic compound. And in the beginning of chapter 16, we learn about solubility of those ionic compound or the salt. In this chapter section, we are going to combine both concepts and help us determine the solubility of the ionic compound when increasing or decreasing the pH of the solution. The ionic compounds that will be affected by the changing of the pH would be those ionic compounds that contain acidic or basic ions, such as basic anion or such as acidic cation. The real-world example of coupled equilibria can be found in ocean acidification. Ocean acidification is a phenomenon where the ocean pH become more acidic and have effect on the coral reefs and marine invertebrates. And this is because their skeletons made up from calcium carbonate. Calcium carbonate is sparingly soluble in water. As you can see that this solution equilibrium constant for calcium carbonate in water is very small number. 8.7 times 10 to negative 9 indicate that it's only very small amount of the calcium ions and carbonate ions that will dissociate. Therefore, the skeletons of marine invertebrates that made up from calcium carbonate will stay as solid because solid calcium carbonate will not dissociate much at all in water. However, the rising concentration of atmospheric carbon dioxide is of the concern because atmospheric carbon dioxide contribute to an increased acidity of ocean water. Our ocean is the storage of carbon dioxide gas. Because carbon dioxide gas can dissolve in ocean water into carbon dioxide aqueous, and the carbon dioxide then combine with water to form carbonic acid. Carbonic acid is a weak acid that contains two protons, or what we call is diprotic acid. Therefore, carbonic acid can undergo acid ionization twice to get rid of each of those protons. Now to tie this back, why ocean acidification is bad for marine invertebrate skeletons is to look at solubility of calcium carbonate when the solution pH decrease, which is going to be example 1 here. The first equation that I'm going to look at is the solubility of calcium carbonate. And this equation is the calcium carbonate solid dissociate into calcium ions and carbonate ion. The next equation I'm going to choose is the second acid ionization. The reason why I choose this because the common ion that we see here is the carbonate ion. In this equation, we see the carbonate. In this equation, we also see carbonate as well. That's why I'm going to pick up these two equations and we are going to combine them, or we are going to couple them. But before we can couple them, we will need to first flip the second acid ionization. The reason why we need to flip this equation is because the second acid ionization is already have carbonate. That's why we choose, and also is produce the hydronium ion as well. The hydronium ion is the identity of an acid. When the concentration of the hydronium ion is rising, that indicates that the solution becomes more acidic. Therefore, in this case, before we can combine the first equation to the second equation, we need to make sure that the calcium carbonate is actually going to react with the hydronium ion. Therefore, I need to flip them. And from what we learned in Chem 122, we learned that when you flip an equation, what we need to do to the equilibrium constant is you will need to invert the equilibrium constant. And here is the result of flipping the equation from the second acid ionization. And here is the result of invert equilibrium constant from the second acid ionization. Next, we are going to combine the first solubility equation with the equation that we just flipped so that the calcium carbonate will react with the acid. And here is the combined reactions between the first one and the second acid ionization, you will see that on both sides, the species that appear on both sides would be the carbonate ions. And after we cancel the carbonate ions, then the equation that you will get would be calcium carbonate react with the hydronium ions, which is the acid, to produce calcium ions, hydrogen carbonate, and water. And from what we learned in Chem 122 is that when you combine the equation, you will need to multiply the equilibrium constant value to get the new equilibrium constant value. Therefore, the equilibrium constant for this equation that is combined between the first and this one right here would equal to the first one multiplied by this k right here. And you will get the k value of this equation equal to 185. And with two significant figures, the answer would be 1.9 times 10 to the second. As you can see that the Kc value of the calcium carbonate in an acid is a huge number. The high value of the equilibrium constant that is greater than 1 indicate that this reaction at equilibrium is product predominant, which means that the calcium carbonate would dissolve in an acid to become and prefer to become the product in this case. That's why we get a high value of Kc, because there are more product that is present at equilibrium than the reactant. Therefore, we can conclude that calcium carbonate would be more soluble in acidic solution than in the basic solution. So the answer would be in acidic solution for part B. Again, this confirmed by the fact that when calcium carbonate dissolves in an acid, you will see that the Kc value is greater than 1, indicate that the product is predominant at equilibrium, or the calcium carbonate can dissolve in acidic water to form the product more than in basic solution. Another way, and also is an easier way to look at this type of coupled equilibria, is by looking at the ions that come from the solubility and look at whether they are pH neutral, acidic ions, or basic ion. Then we can predict their solubility in acidic or basic solution. For example, if you look at the first equation again, calcium carbonate that dissolves in water, when it dissociates into calcium ion, this calcium ion is pH neutral because it doesn't react with water. If you react calcium ion with water, it will form calcium hydroxide, which is a strong base, which is not going to happen. Therefore, calcium ion will not react with water. Therefore, I don't need to worry about this species because pH neutral, it will not have any effect on the basic or acidic solution. Now let's take a look at the second ion that is formed. Second ion, carbonate ion. Carbonate ion, when it reacts with water, it would form hydroxide ion. Therefore, this carbonate ion is a basic ion. Therefore, in this case, because carbonate ion is a basic ion, therefore, if you dissolve calcium carbonate that produce basic ion in an acidic solution, the acidic solution that contain hydronium ions then will react with basic ion, which is the carbonate ion in this case. And by reacting it, it's going to remove carbonate ion from the equilibrium, causing the equilibrium to shift, because as the acid react with the carbonate ion, the concentration of the carbonate ion would decrease. And in order for this reaction to establish the new equilibrium again, as the concentration of carbonate ion decrease, then the reaction will shift toward the product, making more of the product, causing the calcium carbonate to be able to dissolve more because it's going to dissociate more. Therefore, the solubility of calcium carbonate will increase in an acidic solution. However, in basic solution, it would be the opposite effect, and the solubility of calcium carbonate will decrease in basic solution. Because calcium carbonate can dissolve more in acidic solution, therefore, for ocean acidification is bad for the marine invertebrate skeletons because their skeleton will be dissolved in ocean acidification and causing them to have soft shells. Another example of coupled equilibria is the formation of dental cavities in tooth enamel. The major mineral component of enamel is the calcium hydroxyapatite, which is this species right here, that can very slightly dissolve in water to dissociate into calcium ion, phosphate ion, and hydroxide ions. In acidic solution that contain greater concentration of hydronium ions, the phosphate ion can accept proton 3 successive times. And the hydroxide ion from the solubility of the enamel can also react with the hydronium ions in acidic solution as well to form water. And when we compare between the phosphate equations and the hydroxide equation, we can say that the hydroxide equation is going to be the dominant factor that provides the solubility of the enamel solubility, because the phosphate equation are weaker base than the hydroxide ions. In this case, we are going to consider only the hydroxide ions equation. So if you look at the example where the tooth enamel is in acidic condition when the acid waste of bacteria growing on the surface of teeth, you will see that the hydroxide ions in acidic solution would decrease because hydroxide ion would react with the hydronium ion in an acid solution. Therefore, the concentration of hydroxide ion would decrease. This caused the reaction to shift toward the product to re-establish the new equilibrium. Therefore, the solid enamel would decrease because it's going to dissociate more in acidic solution to re-establish the concentration of the hydroxide ion in order to reach the new equilibrium again. Therefore, the answer for example 2 would be that the tooth enamel that composed of calcium hydroxyapatite would be more soluble in acidic solution. Therefore, its solubility will increase. Therefore, the tooth would decay because there will be less of the solid in this case, and the cavity would form. To help resist dental cavities, sodium fluoride is added to many tooth care products. And how the sodium fluoride help resist dental cavity is that the sodium fluoride will react with the calcium hydroxyapatite to form calcium phosphate fluoride, sodium ion, and hydroxide ions. This calcium phosphate fluoride is also sparklingly soluble ionic compound. It's only partially dissociated into ions according to the solubility equation here. And the fluoride ions is formed. The fluoride is a weak base. It's much weaker than the hydroxide ions from the first equation. Therefore, the fluoride ions would only partially react with the bacteria acid waste, resulting in a less extensive shift in the solubility equilibrium. So the calcium phosphate fluoride will stay as solid because the solubility will not increase in this case, so the cavity will not form. Please practice more of this concept by doing the DIY problem on page 77. The hint for these two DIY problems would be you will need to look at the solubility equations and then looking at the ions that are formed. And you will need to determine what type of acidity of the ions, determine whether it's going to be pH neutral, basic pH ion, or acidic pH ion. And then you can determine whether the solubility would be high or low at basic or acidic solution. Same thing for number 2 as well. You will need to consider these two ions and then determine their acidity, whether they are pH neutral ions, acidic ion, or basic ion. And then you can determine whether the solubility of this compound would be more soluble in acidic or basic solution. The answer key for these two DIY problems would be posted on Moodle. And again, if you have any question, please do not hesitate to reach out to me via email.